Alright, hi everybody. This is a video to do some circular motion problems, some sample problems, so you can go back and review some of these. Some of these are harder than others. Some of these we've seen in class, so you might find them pretty familiar. But let's take a look at some of these. So the most basic kind of circular motion problem I can think of, anyway, is to think about a rock on a string. So you're twirling this rock attached to a string in a horizontal circle over your head of a radius of 1 meter. The rock has a mass of 1 kilogram, and the string will break if more than 50 newtons is exerted through it in tension. And the question is, how fast can you spin that rock before the string breaks? Okay, so let's take a look at this. If we just sketch very quickly the circular path of this rock. So there's our circle. You imagine you got a little rock here tied to a string connected to the center of this circle. And you guys remember from our discussion in class what is going on with this rock. Well, if you're in circular motion like this, you're going to have velocity that is tangent to that path, and you're going to have an acceleration that is towards the center of the circle. We call that centripetal acceleration. And these things are related, right? Because centripetal acceleration, one way to find it is v squared over r, where r is the radius of this circle. So that tells us a lot, because we know about accelerations, and we know that, well, when you have a centripetal acceleration, or any acceleration, that means you must also have some sort of force pulling this thing towards the center of the circle. We call that a centripetal force. And centripetal force can be found by saying the mass, the thing that is being spun in this circle, times its centripetal acceleration will tell you what centripetal force you need to keep this thing moving in a circle. In our case, our centripetal force is equal to tension. That's what it is, the tension in the string, and we have information about that tension, how big it can get. So really, in this way, we can think of this thing and kind of plan out our approach. If we know that the tension needs to be 50 newtons, any more, the string will break. Then we can say, well, from that 50 newtons, what's the maximum acceleration we can get? And with that acceleration, what's the maximum velocity we can get? And then we've answered our question. So let's take a look at how that might look. So if we say 50 newtons of force is equal to the mass that's being accelerated, the 1 kilogram mass, and the velocity, well, we're going to try to find that, so we'll keep that as v squared, and over the radius of the circle, which is also 1 meter. I'm just being lazy and keeping the units out. So in this case, v equals the square root of 50, which turns out to be 7.07 meters per second. That tells us from here what we're going to need to, and we didn't even bother finding the acceleration, we just kind of jumped right to the velocity. That is the maximum velocity that this rock can go. Any faster, and the string can't do what it needs to do to keep this thing moving in a circle, and the string will break. Alright, well, that's one way of looking at things. Let's take another problem here. This one is more of an amusement park kind of physics question. There is a ride called the Turkish Twist. They sometimes give them different names. They all look nauseating to me, but the idea is it's a ride where you spin in a cylindrical room. So let me draw a little cylindrical room here, and if we imagine this thing is going to be spun up, and you are sometimes strapped into the wall or holding on handles or something. So here is the center point, center axis of this room that is spinning. And at a certain point, the floor will drop out, and basically what amounts to is that here you are, filled with cotton candy, temporarily at least, and you're stuck. You're stuck against the wall because this thing is spinning so fast. And now we might make the erroneous connection that, you know, there must be some force pushing against me to keep me stuck against the wall. We'll call that the centrifugal force. Wait a minute, nope, we learned that doesn't exist. That's not what's going on. What is a correct free body diagram for this person? Well, let's think about this. If I just, I'll draw it off here to the side. Here's my little dot representing the person here. What forces are pulling down? What forces are pulling up? Because we're being asked these questions here. Something's pinning us to the wall, and they ask us what force keeps you from falling, what force acts as the centripetal force, and what force is pinning you to the wall? Well, let's find out. I'll do these all in red. Of course, gravity, Earth doesn't care what you're doing. It's going to be tugging on you with your equal to your weight. And what's keeping you from sliding down? Well, you might have guessed it. That's friction. That's friction between you and that wall. If it was a frictionless surface, you'd just slip right down, no problem. But this is static friction because presumably you're not moving against this wall. But that's not it, because this wall is also pushing against your back with a normal force. Okay, now from this free body diagram, I bet we can answer all of these questions. What force keeps you from falling? Well, that is the frictional force, right? That's what's, as the room spins faster, your normal force is going to grow, and therefore so does friction, because if you remember, friction depends on your normal force. Now, what force acts as the centripetal force? Well, that is the normal force. That's the force that's pushing you towards the center of the circle, and that's why if you go faster and faster and faster and faster, you're going to require more normal force. You feel like you're being pushed harder and harder and harder. And that's where it's coming from. If there was a little door that opened up in the side of this wall, you'd go flying out tangent to that curve because nothing would be pushing you into the circle. And what force is pinning you to the wall? Well, that's what I brought up at the beginning. There is no force pinning you to the wall. There are no centrifugal forces. The forces that are pulling you in to the circular path and inertia is all that's going on. It just makes you feel squished. And when you feel squished, you assume you're being pushed on. But that's not the case. Okay, so there's one trip to the amusement park. Maybe you'll try that ride sometime and think about physics before you lose your lunch. Another way we can think about physics is in terms of an amusement park. Here we can look at a Ferris wheel. So this is a little bit different. This was different from what we've seen in class. A Ferris wheel, as you know, takes you on a circular path. Ugh, that is an awful. I gotta do that again. I can't live with myself. One more time. This is YouTube. It doesn't matter. What else are you gonna be doing? There you go. That's a circle-ish. A circular path, and you can imagine, you're riding those little seats, a little basket. Here you are. Hey guys, look at me. There you are up top, and then you can also be at different points. Here you are down the bottom, still doing your thing. It's a Ferris wheel, and we're asked to find what are the centripetal forces at the top and the bottom of this circular path. And you may notice the last time you've ridden in a Ferris wheel that some points you'll feel heavy and some points you'll feel kind of lightheaded. What is going on? Well, let's think about it. What the key is with all of these things is a free body diagram. Let's take a look at maybe the free body diagram for the top first. So what's going on? Well, there's always a force pulling down towards the Earth. That's gravity. I'll write that as mg. But you are sitting in a chair, and that chair is pushing up on you. We can call that a normal force because it's normal to the surface. And that's what's happening. Okay, so far so good. Now let's do a free body diagram for when you're at the bottom. Well, what do you have? Gravity still doing its thing. I'm trying to draw this arrow exactly as long as this arrow was because gravity doesn't care that you're on a Ferris wheel. It's just going to tug on you the whole time. But something else is going to happen. You are being pushed on by your seat, and I'm going to draw this vector a little bit differently. This is a longer vector than this vector. How did I know that? Well, because I know something about circular motion, I know that in each case, you're going to have a centripetal force pulling you towards the center of the circle. In this case, at the top, your centripetal force at the top doesn't have to be just one force. It can be a combination of forces. In this case, the weight is pulling down, but there's a force that's pulling up too. That's the normal force. It's the difference between these forces. It needs to have a net force towards the center of the circle if you're going to go into a circle. And since here you notice the normal force is less than your weight, you're going to feel light. This is the point where writing is fundamental. Where you feel light. Like in an elevator. We've seen this sensation before. When your normal force is less than your weight, you're going to feel light. And that's because your weight is doing the work of pulling you. It's acting like the string pulling you in this circle. As a little aside, for those who are really jazzed about this stuff, When you go really, really, really fast, you could imagine there's a scenario where all of a sudden your normal force equals 0, where you just kind of coast in your chair until you fall back down on the other end of the circle, right, just before you get thrown out. In this case, when the normal force is 0, what you have is your weight is the centripetal force, which means it's equal to mv squared over r. And since your mass cancels out, you can actually solve for what velocity that is. Turns out to be the square root of rg. That is what you need to do to find out how fast does this thing need to spin around until you are just coasting through the top there. But that's kind of an advanced aside. I just wanted you to see that. Okay, what about what's going on at the bottom here? Let's take a look at this. Just like up here, you follow the path and then you come down here, you need a centripetal force towards the center of the circle there too. I goofed. It should have been just as long as the other one. You need a centripetal force always towards the center of the circle if you're moving in a circle. In this case, the centripetal force at the bottom is going to be different from the one at the top. It's going to be a combination of these two forces, but my normal force is now bigger than mg. And since mg is bigger, I'm going to feel heavy. And see if you feel the sensation next time you're on an amusement park ride. Next time you're on a Ferris wheel, you're going to feel heavy at the bottom. Why? Because this normal force has to cancel out your weight, right? It does that with part of this vector. It cancels out your weight. But it also has to lift hard enough towards the center of the circle to keep you moving in a circle. And that's what has to happen. So the tug of war between these two forces is really what's going on with the centripetal force. Now I'm going to stop there because I got two more problems that are a little bit tricky and I want to spend plenty of time with those. So take a look at these as you need to.